So good afternoon everyone. I'm Pranav Ashrit and this is my team. We are here to present our major project topic which is a optimization of aerodynamics of bus using 8 channels and taper railings. So as we know, fossil fuel scarcity has increased and carbon NOx emissions continue to rise. Electric public buses, being a promising alternative, remains costly. So we have developed a way to boost the efficiency of the present existing buses by implementing 8 channels and tapering the railings, offering more affordable and sustainable option. Which takes me to the aerodynamics. As we know, aerodynamics refers to the influence of air on an object that moves through it. Any object moving through air is affected and influenced by aerodynamics, which can be a complicated rocket to a kite flying in the sky. So aerodynamics has 4 major forces. There are drag, lift, and thrust, and down force. So considering the buses, drag force is really important. So what is drag force? Drag force is a force that pulls back on something trying to move away from it. So drag provides resistance, making it hard to move. So shape is also important. Shape of an object is also important in terms of drag force. So narrow surfaces usually have less drag than wider ones, and round surfaces usually have less drag than the flat ones. And weight region. Weight region refers to the space immediately after, behind the object, where there are specific flow patterns and turbulences. Objective. So the goal of this project is to make buses more fuel efficient by improving the design in order to reduce air resistance by adding 8 channels and tapering the rear ends using biomimicry. We aim to make buses fuel efficient and emit less emissions, helping to create more sustainable and public transportation system.
So, as I will tell you about the literature survey that we have conducted during this project. While studying some of the previously published inventions in this field, we found out that many of them have suggested use of spoilers and deflectors in the bus designs, but they are not as practical because it will be very difficult for the buses to move in and around the city. And so our approach is more efficient and productive in that aspect. And also we found out that reducing the drag, we can accomplish around 8% of fuel savings, and streamlining the bus designs, we can accomplish 28% of reduction in the drag coefficient. As we can see, streamlining the bus, we can accomplish around 27.4 to be exact percent of drag coefficient reduction. And biomimicry is one of the aspects which we found out during the study. Its definition stands as taking the inspiration from the nature. Either it can be animals or it can be flora also, to design the engineering structures to achieve the suitable objectives of the design. And also through reduction in the drag coefficient, we can accomplish around 20% of reduction in the power requirements annually, and around 18% of carbon dioxide emissions reduction will be accomplished. And the methodology which we followed can be seen in this graph. Initially, we did the assessment part where we decided which field to focus on, where we took the aerodynamic aspect of the vehicles, and then we did the benchmarking where we took a reference bus design, which will be explained in the further slides, and then we did its our prototype designing in the Autodesk Fusion, and then we did its analysis in the CFD software. We used ANSYS Fluent to be exact, and then we did the simulation results then we created the prototype 3D model, and then we put it in a wind tunnel to do its actual testing, and finally we obtained the results and we evaluated the results achieved in simulation and the practical experimentation to get the idea of error and how much the target we have achieved, how close we were to achieve our goal. Further slides will be explained by Nikhil.
Good afternoon everyone, and I am going to explain about the further process where we first benchmark the existing bus chassis and coach, where we have considered Ashok Leyland Viking 222 inches, which means it is around 5.6 meters long wheelbase, and we have considered the Viking because it was presently used in KSRTC Ashwamedha bus where it is an executive coach, and we considered this bus only because it is the most present mass produced bus, and it is the longest vehicles can be very aerodynamically efficient at higher speeds. Next. And this is the bus design. This is our proposed bus design where we use air channel at the front, mimicking the fish gills, and taper the rear end to mimic the fish tail. And these are the bus dimensions exactly. And these are the isometric view and air channels where we can see the path of the airbus, and we have left a small cut in this air vent because during the turning of the wheels it should not interact with the vent. And we have done the simulations in ANSYS Fluent where we have considered airspeed about 80 km per hour, which is 22.2 meter per second. And this is a conventional bus model where we tested the first base conventional model. We got the CFT around 0.069 and drag force of 1600 Newton. And further we tried about only single part of our changes, that is front vents only, and these are the variants. We considered parameters of varying the length of air channel and the inlet shape. This is the front vent 1M. 1M represents 1 meter of the air channel, and 2M, 3M as in accordingly. And there is another version square inlet. And these are the following frontal area pressure plots and the velocity plots, where we can see there is a huge wake region behind the buses because there is no tapered rear end and only vents, and this is the only tapered tail section which we removed the front vents, and there is a massive improvement in the reduction of wake region, which also improves because the CD is reduced from 0.69 to 0.467. And this is the front vents, round inlet and tapered tail. Because why we selected round inlet? Because it is compact in size and less intervenes the driver control modules. And we got the best CD value of 0.362, which is the best we got, and a drag force of 884 newtons. And this is the same version with the square inlet, which takes more space in the driver control modules, and it has got the CD of 0.5868 and drag force of 1200 newton. And this is the mesh report during our simulations. And front vents taper tail has a better number of elements and number of nodes because due to its round shape and taper tail. And we have got, this is the simulation results of all the variants we tested, and the front vents and taper tail has the best CD and less drag force. And this is the graphical representation.
Thank you. And this is all about the theoretical part. So now proceeding for the actual prototyping and testing of the model. What we did is we 3D printed the models that we have taken, that is the conventional model and also the tapered rear section model. So what we use is polylactic acid, that is the PLA, which is very economical and cheap to manufacture. Slides. So as we can see, we have done a cut section model where we have taken the front half of the vehicle as separate and the rear half of the vehicle as separate. So with this design, what we can do is we can change just the front part with the different vents, or change the tapered section as different parts and make mismatch and check which is the most efficient model. And as for our time constraint and project restrictions due to the timeline, what we did is we went with the best, that is the model with the least CD and least drag force. Next. So these are the models that we have 3D printed. This is our conventional model and this is our prototype, that is with the round vents and tapered rear section. So as for the internal testing, what we did is we have given it 3 tappings. The 1 represents the front of the bus, and the 2 represents the rear of the bus, and 3 is the side vents. So what we did is we have given a 1.5 mm holes in the front of the bus, side of the bus, and the rear of the bus, so that we can take the manometer reading to check the pressure of the front, rear, and also the sides. So using this pressure difference, we can calculate the CD of the bus. So this is the testing of the buses. This is a conventional one, and similarly we followed with the prototype. This is during the wind tunnel testing. So it was around roughly 800 RPM, which translates to around 22.3 meter per second, which is roughly around 80 km per hour. So this is during our testing of the conventional bus. So as for the results, what we found out is for our prototype model with the vents round and tapered rear section, we got CD of 0.362 in ANSYS. But when we did our internal testing, we got it as 0.464, which is around 20% error. And for our conventional model, we got it as 0.693 in our ANSYS results, and when we did the internal testing, we got it as 0.769, which is around 10% error. So total drag reduction in just these models, that is internal testing, we have got it as 39.67%. So using that value, what we did is we kept the rolling resistance of the vehicle as constant, because we are not changing the rolling resistance of the vehicle. What we did is we changed the drag force and we combined the both, so we have the total resistive forces. Using that, what we found out is there is 29% of range increase and 29% of mileage increase, and similarly we have 29% of cost reduction of the running cost reduction. And as per our project timeline, we started it in 8th of August, and we did our planning till 28th of August itself, and then we started about researching and doing literature survey. That was from 28th August to around 3rd or 5th of September, and then we did our design and simulation for around 60 days, and then we did our 3D modeling and testing for 10 days, and follow the remaining calculations and results verification for another 10 days, 5 days. Thank you. And the references appear. Thank you.